recording it, and later on, I try to upload the recording to our SFP UQ YouTube channel. Is that all right?
Fine, fine.
Yeah, very cool.
It's okay.
So let's officially start it. So welcome to our seminar today. We are really glad to have you to join our seminar today, the steel timber composite beams and the thermomechanical performance and further research directions. So this events are co-hosted by the SFP New Zealand chapter, SFP University of Canterbury students chapter, and the SFP University of Queensland students chapters. So our key speaker today is Dr. Sébastien Durif from the Polytech Clermont, who is an expert in steel structure and leading a national project on the steel TLC composite floors. And the second presenter is Dr. Antoine Béreyziat. Is from the Scientific and Technical Center for Buildings, who research focused on the thermomechanical behavior of steel timber members under fire conditions.
Hi, Antoine and Sébastien. My name is Stavros. I'm the Vice President here at the UQSFP Society. I just want to thank you also from my end for making the time to present, despite the difficulty with time zones and all. And also extend a thank you to Jeremy Chang from Holmes, New Zealand, for actually connecting us with you guys and for today's webinar. I'll pass the baton back to Zeroy now. So thank you both again for making the time to present for us.
Thanks, Stavros. So without further ado, Dr. Sébastien and Dr. Antoine, the virtual stage is yours. Thanks.
Thank you. Hello. So hello, everyone. Thank you for the invitation. And many thanks to the organizing team for this webinar. So my name is Antoine Béreyziat. I work at CSTB, and I completed my PhD in 2022. And today I'm going to present you my thesis research. And next, Sébastien Durif will present you some work in progress in France on a very similar subject. So I'll start by giving you a bit of context. Before going into more detail, let me explain you why we chose to combine wood with steel. So when we look at the property of this material, it becomes clear that they can be combined to make them complementary. First, steel is highly ductile, whereas wood has a near brittle failure. Moreover, steel is non-flammable, whereas wood is combustible. But the fire resistance of steel is very low because of its rigidity and strength decrease sharply when its temperature rises. And on the contrary, thick wooden elements have good fire resistance. Finally, steel elements are vulnerable to instabilities, warping and buckling, while wooden members have large cross sections. Steel and timber also share common features that make them compatible. They do not require water in the building process, and they are suitable for off-site construction. Here I have some example of mixing of timber and steel in structural member, truss beams, I-beams, press-tested timber, reinforced timber. I pass fast on this example, flitch beams, on the large variety of profile with wooden members. They are already building existing with this kind of process. Sorry. CLT, Sébastien will tell you more after. And faced with all these possibilities, we have chosen to focus on solutions with outward sections, mechanically assembled with wooden beams. Preliminary studies on this subject were performed in 2016, and the aim of my thesis was to take these studies a step further by integrating fire situation, fire resistance. I will now move on the structural analysis of the studied beams. Here you have two configurations, an I section and a T section, each connect with two wooden beams using bolts and screws. For the I section, an elastic linear calculation shows that 90% of the stiffness of the composite beam is attributable to steel, while wood has very little effect on the beam stiffness. For the T section, the stiffness of the composite beam exceeds the sum of the stiffness of its component, steel and timber. It is what I call a composite action. It results in a stiffness gain of 7% in this case. This is only possible if there is an eccentricity, a gap between the neutral axis of steel and timber element. If there is a connection with non-zero stiffness that transmits longitudinal shear between steel and wood. In the case of the I section beam, the neutral axis coincide, so there is no composite action. Whereas for the T section beam, it would be interesting to further increase the stiffness gain by increasing the eccentricity of the neutral axis or by increasing the stiffness of the steel wood connections. But unfortunately, when we try to do this, we generate cracks in the wood, as you can see in this example. And the failure of the composite beam occurs prematurely, and we lose the interest of the composite action. So the stiffness gains that can be achieved are necessarily limited. That's why I chose to focus on configuration with no composite behavior, an I section associated with two wooden beams with no transmission of longitudinal shear between steel and wood. In this case, vertical loads are transmitted from steel to wood by simple contact, and we use the metal chims to ensure good contact between the top flange and the wooden element. Here are the configuration we studied, so two composite sections and their components. We tested this beam with a span of 4.3 meters in 4-point bending. The loading system looked like this with lateral support against buckling. So here you have the load deflection curve obtained for the steel section taken alone. Then there are the wooden beams. The ring failure is here you can see that the failure is brittle, caused by shear and longitudinal tension. In the case of the composite beam, we obtain this behavior. So we have an interesting resistance compared to steel. And in this case, ruin is caused by tension failure in wood. But as you can see in this picture, The steel confines the wood, and the failure does not propagate and is much more gradual, leaving residual resistance. After a while, the deformation becomes so great that buckling occurs. But in the case of the composite beam, the buckling occurs much later with less intensity compared with steel-only member. So if I come back to the load deflection curves, I said earlier we don't expect to observe composite behavior for the configuration, the composite configurations today. Therefore, the stiffness of the composite beam is assumed to be the sum of the stiffnesses of its components. So let's check it with this black curve. So we can see that the black curves, which correspond to the superposition of the red and the green curves, have a behavior which correspond to the principle in the superposition principle in the elastic domain. But when the composite beam starts to plasticize, we can see that there is the capacity of the composite beam exceed that obtained by mean of four black curve. Therefore, there is a composite effect that we hadn't anticipated and which appears during plasticization. This phenomenon is also observed for the second configuration. We made a if-EM model to try to better understand this phenomenon. Here we can see that it worked pretty well for steel. Same for wood-only beams. But when we use the same parameters for the composite beam, we can see that the composite effect cannot be simulated. In this case, the load which is not high enough, and wood failure occurs too early. I managed to obtain a satisfactory match by increasing the yield strength of steel and the tensile strength of wood. And I have the same results, the same kind of results for the second configuration. So this manipulation of the model parameter highlight the importance of the composite effect, but does not provide physical explanation of this phenomenon. So further work is needed to fully understand and explain it. Next, let's look at the behavior in a fire situation and how timber can be used to protect steel against fire. This idea may seem counterintuitive at first, given that wood is combustible. However, it is also an insulating material which burns relatively slowly. This idea is not new, as tests have been already performed in the Netherlands or in Japan, for example. And this principle is already used in some building in Japan. Japan only, as far as I know. Timber also contain water, which helps protecting steel against fire. It allows to keep the temperature of steel at around 100 Celsius degrees for several minutes. This phenomenon is explained by the mass transfer that takes place in wood because of the temperature and the pressure gradients that occurs in a fire situation. So some of the water containing wood evaporates outside, and another part migrates inside the wood. This migrating water will eventually reach the metal plate and accumulate, which explain the temperature dwell on the steel temperature measurement. This accumulation phenomenon has already been observed by X-rays on bolted assembly, as you can see here. So we tested these configurations during unloaded fire test, two unloaded fire tests. Here we have fully protected configurations, more simple geometries, and finally a configuration in which steel is partially exposed to fire. The test specimens were 80 centimeters long and were exposed to fire on 3 or 4 sides. In the first test, 18 specimens were exposed to a standardized fire, ISO 834, for 34 minutes. The fully protected profiles were covered with a 30 millimeter thick bolts, timber bolts. In the second test, 15 specimens were exposed to the fire twice as long, and the timber thickness was extended to 50 millimeter. First, the measurement showed that the thermal protection provided by wood is effective. For example, for this configuration, steel keeps below 200 degrees for over 30 minutes when using 30 millimeter thick bolts. This time rise to over an hour for 50 millimeter thick bolts. And during this time, the steel remains intact. Secondly, we can see that the temperature dwell at 100 Celsius degree for several minutes, reflecting the beneficial and non-negligible action of the water contained in wood. Thirdly, we can see that specimens tend to keep burning during the cooling phase. It has been noted that hollow configuration like P or R tend to lead to severe wood combustion. You have peak here and here due to the highly high-rated structure. Fourthly, on this graph, you see that configuration partially exposed to fire, with steel partially exposed to fire, are obviously less effective, but they offer a certain protection. As you can see, the steel remain below 500 degrees Celsius degrees after around 30 minutes. So it's non-negligible protection. If the profile were completely unprotected, it would reach this temperature in just 10 minutes. Regarding the wood temperature, I would like to speak about instrumentation. We investigated different measurement methods regarding the orientation of the thermocouples. So the thermocouple can be placed parallel to the isotherm like this, perpendicular to isotherm on the cold side, or on the hot side like this. Here are the temperature obtained for a measuring point at 28 millimeter deep depth. And you can see on this figure that the results are very different depending on the orientation of thermocouples. A comparative study based on test result and simulation indicates that the thermocouple must be placed parallel to isotherms like this. So from there, I had reliable test results on the valid model. We can see here, for example, that the test simulation match is satisfactory, which enabled me to go further with thermomechanical analysis. So we did two loaded fire tests. The configurations are the same as those tested at room temperature. And the test setup was like this. So you have the tested beam, the supports, then the cellular concrete slab used to close the furnace, the loading beams, and finally the hydraulic jack that apply a constant load during the fire explosion. Three things are measured: temperature, time, and midspan deflection. We chose to apply a loading corresponding to 40% of the ultimate load. But finally, because of the weight of the test setup, the moment applied to the tested beam corresponded to 43% of the ultimate load. At the same time as this full-size beam, we tested the same configuration, but on an unloaded 1 meter long beam in the same test to see if the mechanical loading has an influence on the temperature. And the answer is yes. This is clearly seen in configuration 2 by looking at the temperature of the steel at the bottom flange. There is a big difference between the unloaded beam and the loaded beam. In this case, a sudden rise in temperature can be seen corresponding to hot gases coming into contact with the steel, indicating that the wooden protection at the bottom is no longer sealed, or maybe even completely degraded. So the progressive degradation of the lower part must be simulated to obtain satisfactory simulation results. In addition to temperature measurement, we also measured the development of the deflection. And above a certain value, the beam is considered to have reached failure. So here you can see how the beam testing test 1 was after reaching failure. And here for the test number 2. So the bending is quite important. So here I show the evolution of the deflection over time, measured during test 1. We can see that deformation accelerates around 25 minutes, and we consider that the failure occurs after 29 minutes. For the fully protected configuration, we obtain this curve in red, and we deduce that the beam has a fire resistance of 81 minutes. By way of comparison, I calculated the fire resistance of an unprotected metal profile with the same loading rate, and the result is a fire resistance of 13 minutes. This shows that the composite beam can achieve an interesting fire resistance time, even though the load supported is greater. To refine the analysis, I try to model this thermomechanical behavior. It works thanks to a thermomechanical coupling and temperature-dependent material properties. For steel, I introduced a coefficient of expansion and also implemented temperature-dependent reduction in moduli and yield strength. The expansion of wood is negligible, but I have introduced a reduction in its modulus of elasticity, shear modulus, and strength. So this has produced a good result, as we can see that we have a satisfactory test simulation match. And building this model was also an opportunity to play with parameters. And for example, I wanted to see what the result would be if we considered that wood solely as a provide protection against fire, but has no mechanical role to play. So here we obtain a deformation curve like this one, and we can see that we lose a few minutes of fire resistance. This means that wood not only protects steel thermally, but also acts mechanically, taking on load that steel is no longer able to bear because it's too hot. So, in conclusion, I would say that we found an interesting composite behavior of the tested beams in the electroplastic domain. Timber seems to be confined by steel, while steel is reinforced against buckling by wood. The ruin occurs because of torsion failure in timber, but the composite beam keeps a significant bearing capacity. In fire situation, wood offer an effective protection to steel. We showed that 45 millimeter thick timber protection results in a fire resistance during 81 minutes. Timber acts as a thermal protection and as a structural backing during fire. Grid care must be given to the assembly joint, which are the weak point of this configuration. And the wooden part tends to burn during the cooling phase. So the post-fire behavior is interesting. And so it seems that the configuration with massive timber elements are safer than hollow configuration. And now I will let Sébastien explain the current and future work on this subject. Thank you very much for your attention.
Thanks very much. We will have Q&A session after the second presentation, but all the audience, feel free you send a message in the chatting box as well. Yeah. I mean, Dr. Sébastien, now I think you can start your part of presentation, and we have like a overall Q&A session after both of the presentation.
Okay, thank you. It tells me that I cannot share my screen. Maybe Antoine, you have to. Okay.
Yeah, I already stopped. Yeah, now you can share your screen.
Okay. Can you remind me a bit how long do we have?
We still have enough time. Yeah, we still have enough time. We have those session booked till 6 p.m. over here. Which means we have an hour. You have an hour, but yeah, so we definitely have enough.
Okay.
Yep.
So I will go just after Antoine to present you the national project on which we are starting to work on. It's called MixAB, which is in French, Mixité Acier Bois pour une construction durable. In English, we can translate it like a composite steel timber solution for sustainable construction. So briefly, environmental data that everyone knows. I just speak especially about French data, where we can say that the estimation of French carbon footprint of a French guy, is estimated as 11 tons of carbon per year, and 25% of it comes from construction. So this led the French government, to develop the environmental regulation called RE 2020, based on the reduction of carbon footprint of buildings. And one of the main of a possibility that is proposed more and more in France is to replace concrete slabs with timber slabs. The question will then be how we're using CLT slabs in composite construction. Another important fact is that the reduction of construction waste as 70% of the waste are from construction in France. So this leads people to think about the development of construction solutions that can be made with demountable elements. So just briefly some examples that inspired us to propose this project. So some works that use CLT slabs combined with a steel profile with mechanical connection like bolts, mainly bolts. And here are some examples. And other researches that were, in this case, based on the study of the fire behavior of the combination of CLT panels and steel sections that were presented here, for example, at WFS 2024. Other developments that were made by different companies, we can see here from Peico, Finland company, who is developing and developed a composite structure made of a steel section, a channel steel section fulfilled by concrete and linked with CLT panels to ensure kind of fire protection. No mechanical action here, just in order to, they made some studies to validate the fire protection of the CLT panel on the steel section. And now also rather new works that are proposed by the WSP and in collaboration with the University of Warwick, where we can see that they are working on clearly a combination of steel section, CLT panels to propose a kind of composite structure that works well. So the main subject that we wanted to work on during this project are the development and mechanical study of demountable steel CLT composite floor and its evaluation of its behavior, fire behavior. So the two main issues are to propose a kind of low carbon footprint solution and also demountable solution. In this project, we have three partners. The first one is Institut Pascal, which is my laboratory based at Clermont-Ferrand in France. Two others are also French laboratories based at Lyon and Saint-Étienne. Just to remind that the PhD thesis of Antoine was made in collaboration between Clermont-Ferrand and Saint-Étienne, the LTDS, with my colleague Maxime Audebert and the CSTB. So the project will be divided in four main tasks. The first one will be focused on the mechanical behavior of the steel CLT composite beams. So we will make, and we have already made some experimental tests and developed a finite element model. The second task is dedicated to the thermal behavior of these kind of solutions, and especially a slim flow configuration. And the third task will be dedicated to the thermomechanical analysis. And finally, we will finish the project by doing some full-scale thermomechanical tests. So as you can see, it follows a bit the same logic as the PhD of Antoine, but a bit wider scale. So the project has begun on January 2023, and it will last 5 years with a total of financial support of 600,000 euros. So the first work package is undergoing. We started with a master thesis, which then continued to a PhD. So his PhD thesis of Saleh Zahafouri started at October 2023 and is still undergoing. The two other tasks, mainly on thermal and thermomechanical behavior, is just getting started. We had a postdoc who started to work on April 2023 until July, so he worked approximately 3 months, but he stopped because he found another job, and so we had to I would say, reoriented the financial support to propose a PhD, and this PhD will start in November 2024, like in 1 month. Normally, we start the PhD on those aspects, and we hope that we will doing the final task through the second PhD that is starting also in the same period in December, more like December 2024. So the project, as I said, is based on the evaluation of the thermomechanical behavior of composite solutions combining steel and CLT panels. The first configuration is more like a configuration which is close to what Antoine worked. The more interesting task for us here is studying the composite action between steel and CLT panel under cold conditions. And the thermomechanical behavior, we will mainly be focused on this configuration, which is a slim floor configuration, and which is more like the same beams that studied Antoine, but just with wider timber between the beams. This was the idea, to get a better contribution of timber in the deflection part of the beam, in the service limit state of the beam. So we already made, for the first main task, we made some experimental tests on steel and CLT panels. Here, the CLT panels are directly bolted on the steel section, and in this case, we considered that the panels were perpendicularly disposed on the steel beam. So you can normally see that we have 3 panels on the beam span. Alors, pointeur laser here. So the first panel, a second one, and a third one on a beam that is approximately 3 meters long. So the idea here was to evaluate the composite action, the influence of the contact between two CLT panels, and how bolts behave inside the timber. A second configuration studied was monolithic CLT panels. So when you have the CLT panels that is in the same direction as the steel section. So here is the first case. The CLT panel in the same direction of the beam. So the CLT panel alone, the steel section in orange, and the combination of both in blue. So we clearly see an important increase of strength, an increase in stiffness, but not so important as we lose a lot of stiffness due to the mechanical connection with bolts. But we clearly observe a high increase in strength due to the composite action. So here is another comparison where we could clearly see here for the second case where you have 3 blocks of CLT panels. Here we don't see like previously, where here we had a clear difference of stiffness, initial stiffness. When we have 3 blocks, initially we can see that we have the same stiffness as the steel section until the blocks get a good contact between all of them and then start to get a composite action. And then we can see that ultimately, as a ultimate state, we can clearly see that the composite action leads to very high strength, but clearly a limited improvement in stiffness due to this type of connection. Here is a comparison between the numerical model that is being developed, where we can calibrate the model on this experiment, but it's still undergoing. For example, here we don't have any degradation in timber inside this model, so we have to to continue the development of this tool. The second configuration that is studied mechanically is the configuration of slim floor, and we prepared two main configurations. The first one is using HEA sections, and the other one U section. As normally you have here another timber floor slab, and also here. So the best configuration should be the U section, and we just wanted to a bit compare both of them. The tests were made just in this August, so we have rather new results. So here are the experimental tests of the steel sections, and here the combination of steel section and CLT panels. The load here was applied directly on the steel section. The idea then will be to compare also when we apply the load directly on the timber slab. So we reached the failure. We chose the CLT panels in order to get a kind of equilibrium between the steel stiffness and the timber stiffness. So we could see that it was rather equivalent, and we could see that in the end we have clearly, as for the steel and timber beam, we have a great combination of both of them to get the behavior of the slim floor. The second one with the UPE works rather similarly, and we can see that we reach clearly a great behavior even after the plastification of the steel section, where we can see that here we follow clearly the stiffness of the CLT panel then until the failure. So again, the numerical model has been proposed and compared to the experimental test, and then can be used to make some comparison, first to evaluate the influence of the contact and the connection between the CLT panel and the steel section, just to ensure that this contact does not act a lot in this behavior. And clearly we could see that if we make kind of glued contact between the timber and the steel, and if we just let friction contact, we reach exactly the same behavior, which was really expected. So then I will pass to the second task. So the first studies that we made during the postdoc. So during the 4 months that during when the student could work with us. So we made some tests in a furnace. We have a very small furnace in another part of our lab, which is about 1 meter, 1 meter per 1 meter per 1 meter wide and high. 2 burners, and here it was mainly to evaluate the thermal gradient in the timber slab, and we were expecting to do also the test with the steel section, but we could not afford to get those tests during this postdoc. So unfortunately here I will show you just the results that we obtained for the CLT panels. So it was the same panels that we tested at cold condition with 5 layers. We tried to, as these panels were not fabricated with thermocouples, we had to input the thermocouples after, which is rather complicated, especially if we want to get horizontal thermocouples or thermocouples that are parallel to the other terminals. So this is what we try to use to get as much precision we could get to have parallel thermocouples. So we compared the expected parallel thermocouples with vertical thermocouples here that are much simpler to input on CLT panels, especially if we look at very full-scale test, then it will be rather difficult to install such thermocouples, horizontal thermocouples. So we wanted to get an idea of the difference that we could observe between both of them. And the last one are exposed thermocouples that are really expected to provide very high results and non-usable. So they are the observations made after the test. We have here a clear delamination of the CLT, which was expected due to the glue used in French. Most of the French companies are still using polyurethane glues in the CLT panels, so clearly delaminating glues. So that was clearly observed here in our test, which is interesting for us because it was important for us that we could get delamination and to observe this delamination combined with the steel section and the impact on the steel then thermal gradient. Here you can see some vertical thermocouples that remain in place, whereas the horizontal thermocouples in the layers that fold down fold with the layers, which lead to some false results in the end for some cases. So here are some observed results of thermal temperatures. So we could clearly observe the delamination and the fact that globally, horizontal and vertical thermocouples gave here some similar results, but we remain with a lot of doubts on the precision of those horizontal thermocouples, as the process that allowed to install these thermocouples was not judged enough precise. So further tests will be done during the PhD thesis that will be that will start at November, where we will try to install the thermocouples before the process of construction of the CLT panel. So here's a summary of what I said. So difficulty to compare parallel to isotherm measurements and unexposed measurements. And we could clearly observe the delamination of CLT slabs even for such small samples. So the next step, as I said, will be to study the thermal gradients inside a steel section that will be installed in a kind of slim floor configuration. And the objective is to evaluate various protection that we could apply on the bottom flange of the exposed flange of the steel section. And the second objective of the PhD thesis will be to prepare the full-scale beam test that will be led at the laboratory at ENIS, who has a bigger furnace which allow to test to make thermomechanical tests on beams of about 2.5 meters long. Okay, so thanks for your attention. Here are the different partners, the colleagues that are working with me on the project. So at Clermont, and UCBL is the University of Lyon, which is with Bruno Jurquiviez. And finally, Maxime Audebert, the colleague of ENIS at Saint-Étienne, worked also with me on the PhD thesis of Antoine.
Thanks, Dr. Sébastien, and thanks, Dr. Antoine. Really good, really interesting research and really good presentation. And now we move on to the Q&A sessions. We already got 2 questions for Dr. Antoine. I noticed you already answered it in the chatting box, but for the audience later on and the audience here, I still try to read it. So the first question is, did the term outcomes support using the Eurocode char rate to calculate the required thickness of the timber as an insulate layer to protect the steel? That's the first question for Dr. Antoine.
Okay. The Eurocode 5 calculation method for the charring rate and charring depth give a good approximation of the time the steel will begin to heat, and we observed that, and we can calculate it, that steel, the composite beam fails a few minutes after steel has begun to heat. So it's a good first design approach to estimate the time the protective layer will burn, and it gives a conservative with a good security coefficient of the time the composite beam will stand against fire. So and I can add that if the advanced calculation method given in the Eurocode 5 is used, it gives also good results, more precise results. But you have to take care of the assembly gaps when the deflection of the composite beam become large. The gaps are opened, and in this case, in this configuration, we do not master the charring rate in the near the assembly gap. So it can we have to be very careful about this joint, but I would say that it gives a good first approximation at the beginning of the fire explosion.
Thanks, Dr. Antoine. And the second question is like for the massive timber configurations, with the steel being fully encased with the timber all around, does each of timber element secure it on or around the beams?
The timber elements are just mechanically fixed using screws that pass through the steel parts in pre-drilled holes, which are oversized. So the assembly is secured, but there is no shear transmission through the screw. So it's just an assembly which is not structural. Maybe I can share a picture. Yes, I have a good one here. So do you see my screen?
Yes, ready. Yes, ready.
Okay. So here you can see, sorry, it's in French, but here you can see the screw with oversized holes in the flange and in the web of the beam. So they are very thin screws which don't have any structural resistance.
Thanks, Dr. Antoine. And we got a question for Dr. Sébastien from Yohito. He's an exchange PhD student to our group. He's from Chiba University in Japan. His question is how those edge-shaped beams connected onto the CLT slab, and he assumed the strength and stiffness of the composite slab is highly depends on the connection configures.
Yeah, exactly. You're perfectly right. Just to precise, so if we are talking about this case, here we just have bolts, steel bolts, M16 bolts that are regularly spaced along the beam. So here, and even as this in this case, or in this second case where we have a monolithic CLT panel, we have M16 bolts. That's all. So we have some initial gaps between the bolts and the upper flange of the steel, initial mounting gaps that are close to 1 millimeter. But in the CLT panels, normally we have very, very small gaps, but very neglectable. But the main problem of this connection is the degradation of timber around the bolt, as timber is very will deform a lot around the bolt, and we are just studying here if we are able to model this behavior, and if then propose some alternatives, and these kind of alternatives, some companies found out some solutions. Clearly here, one of the best way is to consider kind of complement material that will make this connection. The problem for us is here it's not demountable. So we are looking at solutions that offers higher stiffness but remain demountable. But we will clearly look at things that are close to things like this. This is in the case of a configuration where we have, I would say, the standard configuration, when we have the slab above the steel section. About the steel section. In the slim floor configuration, we didn't have any connection. The idea was exactly the same as for the thesis of Antoine. Here, as the center of gravity of both are very close, the one to the other, the connection shouldn't play a role. So we just input a kind of steel plate, you can see here, just at the loading points here to be sure, because we are loading in this first case, we are loading on the steel section. So to be sure that we have transferring load between the steel section and the CLT panel, we input these steel plates. Sorry, here. But later on, we will be doing tests where we load directly on the timber slab, which is more realistic in the real case. And in this case, we will not need any plate at all. And we will try to see if we have any kind of problem here and if we have good load transfer. We just had some dowels here, but again, with the wider holes in the U section to avoid any shear transfer by this these bolts or dowels. Just to be sure that the U section do not fail by torsion. That was our the possibility for this section. So here we had just a dowel here, but it was just to prevent the lateral torsional buckling of the U section. But even here, no connection at all.
Thanks, Dr. Sébastien. Is anyone have further more questions? Feel free to send in your question in the chatting box, or just feel free to unmute yourself and ask the question you want to ask.
Sorry, just one question. Just starting from the presentation earlier, Antoine, you showed some significant cracking in the mechanical test, which is under the ambient temperature. And I'm wondering whether there's any suggestion to overcome that, and especially in fire, if cracking like that happens, then that's not good for fire at all.
I would say that in fire situation, the load due to the fact that it's an accidental situation, the design load is lower than in a normal situation at room temperature. So this kind of loading is not the design approach can't occur in a fire situation. And during the tests, the fire test, we did not observe any crack in the timber. It's more the failure pattern was more charred wood at the timber steel interface and the steel edge bed, but no significant shear crack in the wood during the fire, when exposed to fire.
Thank you.
Hi, Antoine. Thanks for the interesting presentation. I've got two questions. The first one is, well, very interesting piece of work, first of all. The first one is, what was the driver behind using wood as protection for steel? My understanding, based on your presentation, the driver is that trying to increase the stiffness of steel. Because from my point of view as a fire safety engineer, adding wood, although it sounds great from a structural perspective, you're creating a fire safety issue, which is the ignition of timber having a combustible material adding into the fuel load. But obviously, done in moderate portions, it can be worked out. But from I guess, I would say, legislation point of view, it might be difficult to push getting that approved, just by virtue of timber being combustible. But yeah, I would be interested to see what was the driver in that, because it's very interesting and it's promising. And the second question is, I wasn't very clear on the failure criteria of your second thermomechanical test, the second configuration that you show the thicker timber lamella, that the timber board that is about 45-50 mil, that you say you get failure at around 80 minutes into the standard fire test, because there's a big difference between the 30 and the 50 mil in failure time. So is the failure looking at steel temperature, looking at deflection of the steel? The rate at which the temperature increases in steel, what was the failure criterion in that case? Thank you.
Thank you very much for your question. I will begin with failure criteria, because I didn't detail that. There is a European standard for bending test, which put criteria in net deflection in millimeter and the deflection rate. And when we reach these two criterion, we stop the test. So it's really the deflection that is our failure criterion in fire.
Okay. So it was So it was purely on steel, on the rate that the steel deflects, and the extent at which the steel deflects. Okay.
And for the issue, more regulatory issue about wood combustion, it's more like a reaction to fire issue.
Yes, correct.
The driver in trying to mixing wood with other material to making to try to find a good composite behavior is in the global trend, where we try to build more taller building in wood, but we can do it with only wood. So we have to mix it with other material. So this is the main driver. And about the issue of adding fuel to your building with wood encased in steel member, it's funny because the first studies which looked to protect steel using timber. In these studies, they tried to keep wood as thin as they could because they were eager that it would add too much fuel. But what I found is that when looking at the cooling phase behavior, it's when you put more wood, it's not it's okay because it's better than just thin cladding because you have a more oxygenated configuration when you put just a thin wood member. So it's better in this case to put a large member because the reaction to fire is better as it needs more time and to burn, and eventually it will stop burn by itself in some case, but we all know that it's complicated to prove that significant each time because it's like a chaotic behavior. We do not really know if it will just stop to burn or if it will continue with smoldering fire, for example. The interesting thing in adding some steel, which is non-combustible, is maybe I did not prove that, but the idea is if we put non-flammable material in the wood member, maybe after the wood is burned, the structure remains because the steel has passed the critical phase of the fire, and maybe we can save structure. There is a post-fire behavior which is interesting with this configuration. That's why I think it was very it was studied. It was developed in Japan because they have a lot of problem with earthquake fire.
Yes.
So the decay phase of fire is important, and maybe steel can help in this case.
So I agree. I think in this case, you're relying on steel more being the structural member and not so much the wood being like, carrying the load in this case. Because usually research I've seen is the other way around, is they're trying to enhance the structural capacity of engineered wood by embedding steel or carbon fiber into the CLT, for example, or your glue lamp beam to increase for example, make the wood less brittle in failure and things like that. But what actually intrigued me in the results was between test 1 and 2 and the standard-fire testing, I see a big difference between the failure time, and you explained that you explained the criteria that you've used. But I also wonder, when you did the fairness test, did you adjust the oxygen that goes into the furnace when the bigger section of the timber was actually flaming and burning? Because we all know the effect of standard fire testing combustible material in a furnace, right? We know the issue that they adjust the temperature curve once you get flaming from the timber to follow the standard fire curve. It would be interesting to see that. I don't know if you do the same type of testing in a different setup, whether the result will be the same or will actually fail at slightly faster in this scenario, or slower. I don't know, but yeah.
In my case, oxygen was not recorded. We did a standard fire test. But you're right, it's an issue for timber building in general. So, but we didn't address this problem in our research. But it's a hot topic in timber construction on fire. You're right that it's an issue that apply to my configuration too. You're right.
Cool. Thank you. Thank you for your time.
Thank you.
Thanks, Dr. Antoine. Is there any last minute questions? Just feel free to send in your question in the chatting box or unmute yourself. And I really like your answer for the second question Taro asked. So it's like from another perspective, it's like the steel was actually the material makes the timber strength or more resilient rather than or you can extend this from both aspects. Like because in your presentation you said the timber was the protect the steel, but actually you can extending this question from another way, like the steel actually try to make the timber the structure elements more strength. I'm understanding correctly your answer.
Yeah.
Yeah.
Yeah. Maybe Antoine, if you want to.
No.
But yeah, that was a bit the idea in the first initial test we made before the PhD of Antoine was generally what we see in literature is how can we use steel to strengthen timber. The idea in our case was to how we can use timber to strengthen steel and strengthen it, especially under fire situation. But it was also to evaluate, we tried also parallelly to this work to look at thinner steel sections to see how timber can avoid local buckling in steel and get really a good combination. But those tests did not work very well. But the idea was clearly from the beginning to use timber as an element that will strengthen steel and especially protect steel. But you can clearly see that in this case, it doesn't provide a lot of stiffness, initial stiffness, but it provides important strength. And this part, ultimate limit state, is interesting, especially in accidental cases, just like seismic or fire situations.
Yeah, that's really innovative and new aspect for me about this question. And any question from the audience?
Sorry, I'm jumping back, Zero. Sebastian, did you mention what was the type of the timber that you used to encase the steel? Was it engineered wood or was it solid? And and what type?
You mean for the PhD thesis or the CLT?
Yes, for the PhD thesis.
The PhD thesis, yeah, it was here. It was engineered timber, I would say, with the different layers of timber to make the beam. How do we say it, Nance? Lamellé-collé?
Laminated. So the 50 millimeters covering or 45 that you talked about, is this comprised of different lamellas, or is it one thick lamella, one thick layer, or is it multiple layers?
I think it's only one lamella, but probably the element that goes in contact with the other one. Can you show us, Antoine?
Yes, I draw the lamella, so it's it.
But this had no structural behavior.
Yes, I noticed. Yeah.
Okay, here you can see the lamella.
Yeah, different lamellas.
So it's different lamellas, because it's you're doing glue lamp. Oh no, I was just thinking, what would the same configuration be if you do CLT? Because CLT you have different orthogonal instead of perpendicular layups. So I was thinking how this would work in a slab instead of a beam, because in a beam you can place the lamellas next to each other. And you didn't, and did you consider and delamination wasn't an issue? Because I remember Antoine mentioning that did occur between the lamella layers
in CLT panels, yes. But there's the glue that are used generally to make glue lamp and CLT are different. And we don't have a lot of problems of delamination for glue lamp beams, but more on CLT.
Is that because of more shear that you get in the CLT instead of the glue lamp, or we don't know the reason why that is?
I have seen researches in Europe with the same kind of configuration, and you have CLT in place, which replace glue lamp. But I don't remember if it was in fire situation. But
it depends on the glue. But now we have more and more non-delaminating glue that are used for CLT. In our case here, we studied the CLT panels that were provided by the company. But it's for us clearly an issue. Will we pursue the works with this kind of glue, or we will go and start to look at the future? That clearly is the future. That will be the using of glue that avoid this kind of delamination. But in France, it's not very widely used because it implies to change the whole process of the companies. So that's why here the companies are not really dedicated to use this type of glue because of the fire regulations that impose to protect the CLT panels under fire because it is combustible. So they don't have a lot of.
I see.
They don't see for the moment the importance to change everything as it doesn't provide a very important change in the global aspect of the floor. But in our case, it's important. And in the solution, I talked about the studies that we will do on the different protection solutions that we could apply on the bottom flange of the steel. These solutions maybe can be an issue also to avoid to protect the CLT panel closely around the steel section to avoid this delamination to occur closely to the steel section to remain protected as long as possible. But the fact is that in the thesis of Antoine, what you could see is that we don't observe any delamination, but we observe the falling of this
of the whole layer,
And also this depends on how we made the assembly of the whole concept. We could have decided another solution to develop this section to avoid this falling off due to the process of mounting. Maybe Antoine, if you want to precise it, because you had another idea that we said no, and maybe could have been interesting to explore also.
Present this quickly. So the idea is that this part can you see my screen?
We don't see the PowerPoint.
Yeah.
We see your screen. Yeah.
Okay.
We only see the notepad. Yeah.
Okay. Maybe you can see the weak point are the joints.
Yep.
So maybe if we can form this piece to just have one joint at the bottom, it's a better idea. Or making the joint more more sinewy, with assembly. It's not a straight joint, but with more complex geometries. And in this case, maybe the joint issues is not so important, and maybe we can even glue the joint to keep it close. That's
I mean,
some prospect. Yeah.
looking at it, I was just thinking, because your individual boards are, how wide are they? Like 40, 50 mil? Like the individual boards that you use, are they like 40, 50 mil wide? For the covering, you have 1, 2, 3, 4, 5, 6. So the individual
Layers?
width of those layers, is it like 40, 50 mil? Looking in the horizontal direction, you said 236 is the total at the covering. The individual ones, what's the width for one of them?
This the width of the liner?
Yep.
I don't remember, but maybe 50 millimeter, something like that.
Yeah. I was thinking the same, because here in Australia they started doing around 80, 85 mil. So the idea that you're presenting makes a lot of sense, that you can split the drawing and you could have maybe 3 of these if they are wider, so that you don't have the whole thing falling. But yeah, it's interesting setup. Very interesting.
But when we talk about fall off, in my case, it occurred maybe 1 hour after the beginning of the test. And in fact, this piece, the bottom piece, was completely charred. So it's normal that it fall. So it's not a really delamination. Just the wood is completely charred. So
I see what you mean. Yeah. So the temperature that you're measuring at the steel flange at 60 minutes, was it 300, 400 degrees or 200 degrees at the flange by 60 minutes, for example?
It's like it keeps at around 100 degrees for a long time, maybe 150. And then this piece fell off because it's completely charred, and then the steel is directly exposed to fire, and the temperature sharply rise. And then when this piece is completely charred, maybe the failure occur 10 minutes after it fall off. So that's why I say that the Eurocode 5 method for calculating the charring depth is a good design approach to evaluate the failure time of this kind of configuration.
Fair enough.
Thanks, Dr. Antoine. Any last minute question, like real last minute questions? We're just waiting maybe 60 seconds, and we're probably going to end today's sessions. Any question from the audience? Well, I think we try to end today's sessions. And first of all, like we really appreciate Dr. Antoine and Dr. Sébastien using your early morning time to presenting your research, and really appreciate of that. And we're going to thank our dear friends from the STP New Zealand chapter and the the University of Canterbury student chapter to collaborate with us to make this event happen. And in the end, big thanks to Jeremy and to contact Dr. Antoine and Sébastien and to make this collaboration event possible. And also really thanks to all the friends in New Zealand using their dinner time to spending their dinner time with us. So looking forward for more collaboration with all you guys, and thanks again, and see you till next time.
Thank you.
Thank you very much.
Thank you, Jeremy, for having making it possible to make this and this webinar. And I hope we will meet again soon.
Thank you. Thank you.
And again, also for you, Pierre-Jacques.
Yes. Yeah. Looking forward to see the results, the future research on
the project.
Steel beam,
Yes.
Yeah. Especially the steel beam connected to a concrete slab, CLT concrete slab with the shear studs, because that I believe is never been tested before. Or
where you have also concrete?
Yes.
This is from a company. This is from a company.
Oh, okay.
That is an example of what is done. But we will probably use it as a kind of inspiration of what we could say, what we try to do, but trying to keeping it demountable. That was an issue for us.
Cool. Thank you.
Thanks, everyone.
And talk soon.
Thank you.
Thanks.